Hello everyone. In this video, I'll talk about what is a stuck at fault model and how to detect such faults in a manufactured chip. After fabrication, every chip goes through production testing to ensure that no physical defects have occurred. To make this practical, simplified fault models are often used, and one of the most common is the stuck at model. In the stuck-at model, we assume that some internal node in the design may be permanently stuck to logic 0 or logic 1, regardless of the actual circuit behavior. In order to apply this fault model, designers have to reason how these faults can be activated at the intended internal nodes and subsequently can be observed at the chip outputs. Let's understand this fault model using an example. Consider the circuit shown here. Suppose in this circuit we want to check whether the node X is stuck at logic 1. To detect this, we first try to force node X to 0. We do this by choosing the input values A equals to 1 and B equals to 1. That would normally drive node X to 0. Then we also set the input C to 1. Since this is a NAND gate, setting C equals to 1 allows any change at node X to propagate at output. If node X is not stuck at 1, it becomes 0 when we set A equals to 1 and B equals to 1. And so the output D is 0. This circuit is a good circuit without any defects. However, if node X is stuck at 1, it will remain at 1 when we set A equals to 1 and B equals to 1, and thus the output D is 1. Since the output over here differs from the expected one, that is 0, the circuit is faulty circuit. Thus, we see that this test allows us to detect whether node X is stuck at 1. Similarly, we can check whether node X is stuck at 0. We can try to force node X to logic 1 by choosing input values A equals to 0 and B equals to 0. That would normally drive node X to logic 1. We also set input C to 1 so that any change at X is propagated to output D. Now let's observe the signals at different nodes. If node X is not stuck as 0, it becomes 1 when we set A equals to 0 and B equals to 0, and thus the output D is 1. This circuit is a good circuit. Here output D matches with the expected output. However, if node X is stuck at 0, it remains at 0 even when we set A equals to 0 and B equals to 0, and therefore output D is at 0. Since the output differs from the expected value, this circuit is a faulty circuit. We can see that this method uses a simple model to find the stuck-at faults in the fabricated chips. However, the next question is, can we always detect stuck-at faults using this method? The answer is no, not always. In the circuits containing reconvergent fan-out, some internal nodes can be untestable. Even if we apply different input combination, the fault effect may never reach the primary output, and therefore it cannot be observed. There are two properties that determine whether a circuit is testable using stuck-at fault model or not. The first is controllability. Controllability is how easily we can drive an internal node to logic 0 or logic 1. The another important property is observability. What it means is how easily a change at an internal node can propagate to the output. A well-designed testable circuit should have good controllability and observability. In a design to perform such tests systematically across all internal nodes, we need a strategy that generates test vectors that are specific input combinations along with the expected output values. These are important to detect stuck at 0 and stuck at 1 faults. For example, to test the circuit shown earlier, we need to develop test vectors, which are values of A, B, C, and the expected output D. There are several industry standard tools for automatic test pattern generation. These tools read the design and generate test patterns used to validate the chip. This is all for this video. Hope this is helpful.